All right. Welcome, everybody. This is a quantum computing from a software perspective workshop. My name is Richard Preston. I am an engineer at the MITRE Corporation. I've been there for about 3.5 years. But more importantly, I'm a Tufts alum. I'm a double jumbo. I got my undergrad, my BS in computer engineering in 2018, and then I did the 5-year program. I stayed 5th year and got MS in electrical engineering in 2019. So yeah, I've just asked everyone to kind of put in the chat who introduce themselves and what level of experience they have with quantum computing. This workshop is intended for those that have pretty much no experience. If you do have experience, it'll hopefully still be fun and interesting. But if you don't, you're in the right place, right? This is hopefully not going to go over your head. We'll try to avoid the math aspects of it. But yeah, just to give a little more background. So MITRE is it's a not-for-profit that operates federally funded research development centers. So it's kind of similar to like MIT Lincoln Labs or Draper, or any of those you may have heard of. But really, the core of what we do is solve problems for the federal government. So it's not a contractor, but it's not working directly within government. It's almost a consulting role. So MITRE has an interest in a lot of technologies, including emerging technologies, as these are going to be relevant nationally. And so I've been doing some internal research on quantum computing and specifically quantum software development for the last 1.5 years or so. So yeah, just to jump right into it, I just wanted to start off with a question. What is quantum computing? Now, a lot of you have already said in the chat that you don't really have a lot of background with quantum computing, but you probably have some notion or some idea about what quantum computing is. So everyone just take a second, type in the chat, what is your kind of current idea about what quantum computing is in like a sentence or so. What thoughts do people have about what is quantum computing? Maybe you've seen like a couple pictures or media reports. Maybe you've seen this, this chip, Google's Sycamore processor. This was the processor that they used when they claimed that quantum supremacy a 1.5 years ago or a couple of years ago. In other words, we can solve a problem faster than anybody else could have ever done it. Or maybe you've seen the cryostat that IBM uses to supercool their superconducting chips to close to absolute zero. So have people seen these pictures or they've never seen them before? I think the cryostat is really cool looking. Using quantum computer to run code. Ooh. Sure, yeah. So certainly, a quantum computer is a computer and computers can be programmed. So that's what we're going to talk about today is are now software frameworks which you can actually write code that can run on a quantum computer. All right, any other preconceived notions of what is quantum computing? Algorithms that follow Schrodinger's cat theory. Love it, love it. Any possible outcome. Something to do with using superposition instead of zeros and ones. Okay, now we're getting there. Okay, so here, why don't we move on and hopefully we can clear up the people's questions. So, well, first of all, starting from because I promised I would give you the software perspective. I promised to give you the perspective of somebody like me has experience coding, but not necessarily like deep into quantum physics. So when we talk about computing, really, and conventional computing or classical computing, really we're talking about digital logic. Virtually all the computers that we have, your smartphone, your laptop, even going back to the ENIAC, which was the first electronic general purpose digital computer, all the way to Summit, which is now the second most powerful supercomputer in the world. Yes, we've made amazing advances and you can do amazing things with computers that we never imagined. But at the same time, it's really all fundamentally the same principles that it operates on, which is digital logic. So what is really important about quantum computing is that quantum computing is fundamentally different. It does not operate on the same principles of digital logic. And this is really the key takeaway. This slide is key to, if you don't remember anything else from the workshop tonight, this is a key thing. So quantum computing is not simply just a fast conventional computer. You can't just take Python code and put it on the quantum computer and it's going to run faster. It doesn't work like that. It is a new way of performing computation that solves specific problems better. So this is really the key point, and we'll talk about what that means. All right, so diving into some fundamental concepts of quantum computing. The first thing we're going to talk about is qubits, which is short for quantum bits. So when we talk about bits in classical computing, this is the fundamental unit of information. It's this binary state called a bit. And bits can take on a discrete value of 0 or 1, off or on, false or true. And they're implemented in physically, right? So you could have like a computer chip where a bit is implemented as an electrical signal, and which can be either high or low voltage. There's other ways of implementing bits. This is like a really common way. And again, taking the software perspective, in software, we're talking about a Boolean value, very simply, right? So if you've ever done any programming, heard of Boolean value, that's what we're talking about, true or false. Okay, so again, I said quantum computing is totally different. So in quantum computing, the fundamental unit of information is a quantum state, not a binary state, called a qubit. And qubits, as Matthew alluded to, can be 0, 1, or some combination of both, which is called a superposition. And again, qubits, just like bits, can be implemented in a variety of physical systems. But so depicted here is an electron, which could be spin up or spin down. And there's other ways of implementing a qubit, right? A popular one is a superconducting circuit. But in this case, we're talking about electron. And what we say is that before we measure the electron, it could have a spin in superposition of up and down, which means a combination of both at the same time. So if that's very strange to you, I don't blame you, but this is just how quantum physics works. Or we have these systems which we can have discrete states when measured, but while they're bouncing around and doing whatever they're doing, when we're not looking at them, when we're not measuring them, it can be in a combination of both, and it's actually a linear combination of both states. And we'll talk about what that means again. The analog to software, and this is a analog that it's actually not that popular, not that talked about, but I find extremely helpful, is a qubit is like a data structure with 2 floating point numbers. So you have some structure, some unit, let's call it X, all right, and it has some amount of zeroness and it has some amount of oneness. And I find that to be a really useful way of thinking about it. Is anybody confused about this or questions about this, or like, how could that be? Or people following? You can give me like a thumbs up or a stop sign or something. I don't know. You can do the reactions in Zoom, I think. All right, I'm getting some thumbs up, so that's good. Okay. So moving on or deeper into what a qubit is and how we express it. So when we talk about qubits are expressed mathematically as a vector. So if we go back to that previous slide for a second, I said that a qubit is like having some amount of zeroness and some amount of oneness. This is like an ordered pair. So if we plot that on a graph on a Cartesian plane, we have the zeroness on the X, or I guess it would be this way for you guys, zeroness on the X and oneness on the Y. Then we can say the qubit 0 has 100% oneness and 0% zeroness. So if we go back to this data structure, the zeroness would be 1 and the oneness would be 0. So that's the point 1, 0, the vector 1, 0. Similarly, the 1 is expressed as a vector 0, 1 because we have no amount of zeroness and 100% oneness. And we can, as I said, we can have a superposition of these. So an arbitrary qubit is somewhere along this unit circle. So we have a 0 component and a 1 component, and the coefficients of each. These are actually called the amplitudes. A and B are called amplitudes here. But we have the constraint that A squared plus B squared has to equal 1. And talk about why that's the case in the next slide. Does this make sense to people? All right. So here's a key point. When a qubit is measured, it becomes a 0 or 1 with probability equal to the amplitude squared. What that means is if we have, again, this arbitrary qubit, let's say it's AB, when we measure it, the probability that we measure a 0 is A squared, and the probability that we measure A1 is B squared. So given that, why do you think the A squared plus B squared has to equal 1? Any ideas? You guys can just type in chat. You don't have to raise your hand or anything. Don't answer all at once. I know it's late. Probably can't, yeah. It has to collapse to either 0 or 1, so total probability has to be 1. Exactly. Yep. So so yeah, either we're going to measure a 0 or we're going to measure a 1, and the probabilities added up have to be 100%, right? One thing to note here is that when we measure the qubit, it's not merely that we observe 0 or 1 with a given probability. We do, but when the act of measuring the qubit actually does change its state. This is very strange, but this is how it works. So if I have a qubit that's like sitting out here, AB, and I measure it, let's say I measure a 0. Now the qubit is a 0 qubit. We've actually taken that vector and we've moved it here. Now we can't control whether it went to 0 or 1. It's a chance, it's a probability. But once we've measured it and we measured that it's a 0, now it's a 0. Which is, again, it's weird, but that's just how it works as per our physical observations. Okay, any questions on this? So here's a little test. So for each of these states, what is the probability of observing a 1 when we measure the qubit? So how about this first one is probably pretty easy. So if we have a 0 qubit, we measure it once, we measure it twice, we measure it a million times, we're always going to get 0. So the probability of measuring a 1 is 0%. Okay, the second one, again, pretty easy. It's a 1. The qubit is already a 1. It's not in a superposition. I can measure it a million times and I'm always going to get 1. So the probability that it measures 1 is 100%. Okay, now here's where it gets tricky. So what's the probability of measuring a 1 with this qubit here at 45 degrees? Yep, 0.5, 50%, exactly. Because 1 over square root 2 squared, remember the probability is the amplitude squared. Amplitude meaning like the coefficient. So 1 over 2 squared is 1/2, which is 50%. All right, how about this one? This one's a little weird. What's the probability of measuring a 1 here? Yep, 3/4, 75%. Notice we have a negative sign here. So this is allowed. Okay, we can have, this is called a phase, which we'll talk about much later. But it doesn't matter because it's squared. So when we measure it, it doesn't matter what the phase is. We square it, and that's the probability. All right, so you guys thought you were going to come here and sit and listen, but you actually have to do something. We're going to now move on and measure a qubit. So I'm going to paste a link here. Let me see if I can copy it. Oh, it's not going to work. I might have to. Oh, it's not. All right, let me get out of here for a second and copy the link for you guys. Okay. Everybody go to this link. This is a This is a Jupyter notebook that you can access online. If you've ever used, it's called Binder. But this is it's kind of like well, it's a repository, code repository called Quantum Katas. Oh man, this is like really bright on me. That's weird. Sorry. Which is basically like a tutorials. Okay, so this is something that Microsoft offers for their Q# programming language, which is Microsoft's programming language for quantum computing. But we're not going to actually do the quantum katas today. We're going to do something slightly more basic or more straightforward, I would say. So what I want you guys to do is go to that link, load up the page, and then create a new Q# workbook, or notebook rather, a blank notebook. So let's see, this is not where I want this. I want this up here. All right, and give me like a thumbs up or thumbs down if you're able to get there or not. You should get something like, it looks like something like this, right? Although it's going to be blank. So you should see Jupyter, and it'll probably be untitled up here. It takes a while to load, takes a little bit of time, so just be patient. But here, I mean, I can go to it and show you. Mine is like a local Jupyter hub or whatever it's called, Jupyter notebook. Still loading. Wow, I must have a better connection than you guys. So it should go to here, and then you just go new Q#. That's all we have to do. 2 clicks. Okay, so you should see something like this. All right, so for those of you, it's still loading. Yeah, try a different browser. If you can't get it to load, then you can still follow along and still learn, but still just try to get it to load, because then you'll be able to actually try it out for yourself. So the first thing we're going to do is a hello world, very simple, okay? And so just we're going to define an operation that outputs a message. So in Q#, the developer, defines operations that encapsulate a set of instructions for transforming the quantum system. Now, the reason why it's worded that way is because it's just slightly different how quantum computers work versus classical computers. So in the context of Q#, this is the syntax they use. They have operations. They also have functions, which is only for classical stuff. If you're not doing anything with qubits, but if you're going to use qubits, you need to do operations. And the syntax, hopefully it's not too unfamiliar. It looks a little bit like C# or F#, or, I don't know, Java. And the only thing that might be a little bit different here is just this syntax. Unit is like void. So it means we don't return anything in the operation. So put this in one of the little like boxes, and then I'll show you. And then you hit play. So if I say, all right, operation, say hello. I know you guys can't see the slides, but this is a simpler one. And then you do message, hello from quantum world, or whatever you want in there. It's just a string. And then you hit the little play button, run. And then now, again, this is a little bit weird. You have to actually simulate it, because it's not enough to just create the operation. When we write simulate, what that's doing is simulating a quantum computer. So we do simulate, say hello. This is what's called a magic command in Jupyter. And you just run that, and then you say, there you go, hello from quantum world. So hopefully, so this is the, taking the already baked cake out of the oven here. So this is what it should look like, right? Something like this. So I'm going to get rid of these guys because I don't need them. Oh, going back to the slide as well here. So yeah, as I said, operations can be simulated on a classical computer. but subject to computational resource limitations, right? I mean, the whole point of quantum computing is that a quantum computer can do stuff and solve problems that a classical computer cannot. It turns out that if you're trying to simulate a quantum computer, it is exponential with the number of qubits that you're trying to simulate with the respect to the RAM requirements, the memory requirements on a classical simulation. So we can only have so many qubits to simulate. If you want more qubits, then you'll have to build a better quantum hardware. So which folder? Oh, it doesn't matter which folder. You just make a new, all we're doing is using a new workbook. This is just, I'm just kind of piggybacking off of this quantum catas system or repo. All right, did everyone get this, the hello world? If you're still loading, it's okay. This one is not that key. This is where we want to get to. So we've talked about qubits. Now we're actually going to measure the qubit. So what I want you guys to do is get to a new box, define a new operation, and you can call it whatever you want. I'm calling it let there be qubits, and allocate a qubit with the use statement. So this is kind of like you're allocating memory in C or C++ or whatever. So you say use qubit gets qubit, and now we've allocated a qubit. And to measure the qubit, you use this M operation, and this will return the result. So you can use let to define a variable, and then you can print the result using this $sign syntax. When you have this $sign syntax, it'll allow you to have braces, and if you put the variable name in the braces, then it will replace it with the value of the variable. And then after you've defined the operation, then you just have to simulate it. So I'll let you guys try that for a second. I can also show it off. It's probably easier to just show it here. So here we are, let there be qubits. I'm gonna hit run. That's gonna compile the operation. If it works here. And then I need to restart the kernel here. Oh, there we go, it worked. And then we can say, let there be qubits, and then it's gonna tell me, all right, I allocated a qubit, I measured it, and then I printed out the result, and it's measured as 0. This is because qubits are in a 0 state when they're allocated always in Q#. Not only that, but they have to be in the 0 state before they can be deallocated, before they go out of scope. If you've ever heard of the idea of scope, basically that means that a variable only exists within a function or within an operation. So in Q#, the concept of scope is here. So if we have an operation and we define a qubit inside it, or we allocate a qubit inside it, when it gets to the end of the operation, it's going to try to deallocate the qubit, but the qubit has to be a 0 for it to be deallocated. So that's important. You're going to get a runtime error if it's not. Okay, did everyone measure a qubit or still working? Getting a couple thumbs up. Please, if you have questions or you want to stop or go slower, definitely want to hear from you, because it's not, I mean, the point is for everyone to be along for the ride. So, okay, I think we're getting some thumbs up. So I will send out the slides after. So if you miss, if you get a little behind or you miss any of these exercises, you can go back yourself and try it out. So, okay, so now we're going to talk about single qubit gates. So going back to, again, the classical computing perspective here, when we talk about how digital logic works and how classical computation works, really it's a series of small decisions performed by logic gates, or the building blocks of digital computing. So the way you can think about that is, okay, we have all these little guys here that are in some chain of causation, I guess, and they're looking at this previous state or the state that they're getting input, and then they're understanding the input and doing something in the output based on what the input was. So this guy is saying, okay, turn on B only when A is on. So, well, A is on, I guess I'm going to turn B on. This guy's saying, okay, turn on C when B is off, or only when B is off. Well, B is on, so I'm not going to turn on C, right? So, I mean, I think probably many of you have seen digital logic gates. If not, that's okay. But this is just how computers work at a very fundamental level. And the way we define digital logic gates is with what's called a truth table, which shows the resulting output for each possible input combination. So here are some of the very common gates. So you have unity, which just outputs the same as the input. So the output is, if the input is A, the output is A. Not, which inverts the input. So if the input is A, the output is the opposite of A. So if it's 0, it's a 1, et cetera. We have AND, OR, XOR. If you haven't seen this before, it's fine. Just the point is, this is how we define digital logic gates. And note that there is a limited number of 1 and 2 input digital logic gates because we just only have so many possible inputs and output combinations, right? Okay, so quantum computing, again, quantum computing is totally different. It works with, or quantum computation is a series of small modifications to the state of the quantum system. And we're talking about small modifications, we're talking about gates, okay? But these are different, slightly different, or work in a slightly different way than digital logic gates. So here it's almost like, rather than having like this chain of causation going down, like one guy is looking at the previous light bulb and turning on the next one, it's more like a factory where we have the qubit coming down the conveyor belt or coming down the assembly line. And we have these robots that are programmed to transform the qubit in a certain way. So maybe, you know, the qubit is a car and it's going down the assembly line, and the first gate is going to attach the door, and the next gate is going to transform the car around or rotate the car around, and the next one is going to lift it up in the air and attach the wheels, right? And then at the end of the conveyor belt, at the end of the whole algorithm or the computation, whatever, that's when we measure. So one thing that is a little bit different with this analogy, though, is that quantum operations are reversible. So the analogy there is like, okay, I have a robot that can put on the door, but if I run the assembly line backwards, maybe I like switch the batteries around or something, then you know it's gonna take the door off. But of course, when you measure, it's all over, right? When you measure, it collapses to superposition. It's either a 0 or a 1, and you can't get it back. So measurement is a destructive operation. Okay, so let's dive into some of these gates. Quantum logic gates are defined, rather than with truth tables, they're defined as matrices that transform the state vector of one or more qubits. Remember, the state of a qubit is defined as a vector. So when we say state vector, that's what we're talking about, right? Somewhere along that unit circle. So the two really, basic ones, key ones that we'll talk about right now is X or naught, which does pretty much what you expect. It turns a 0 into a 1 and it turns a 1 into a 0. But if you think about it geometrically, what it really does is it flips the qubit over this line. So, based on where the qubit is, it's going to transform it in that way. And that's just a consequence of the matrix math if you actually do it out. So I'll send you guys the slides. This will be, extra credit. You can go look at the matrix math for yourself. And this is the circuit diagram symbol here. H is a really important gate called the Hadamard gate. And this allows us to put a qubit into superposition and back out. So it toggles between 0 and the state called plus, which is like 50% 0, 50% 1. And again, if you do the math out, it works out, but we're not going to focus on the math today. Okay, so here's another quiz. What is the state of the qubit after each gate? So we start out as a 0, and then we apply an X gate. So if we apply the X gate to a 0, what do we get? 1, exactly. Because if we go back, we just said that the X gate toggles between 0 and 1. So we started out as a 0, and now we're a 1. Now if I apply the X gate again, now what do we get? What is this? Back to 0, exactly. Notice how we have the same qubit, right? It's like in classical computing, you have like a digital signal, maybe it's a voltage that comes into the gate. The gate like reads the voltage and outputs a new signal based on what it is. This is not that, right? We have one qubit that's going through the whole time, and you're just applying transformations to it. So we've had the same qubit as a 0, now it's a 1, now it's a 0 again. Now we're going to apply H or Hadamard gate. And now what do we get? What is this? Maybe you don't remember. Plus, yes, it's technically this plus state. But if you actually write out the whole state vector, it's this. So it's like 1/√2, 0 plus 1. Because remember, it's like 1/2 0 or 50% 0 and 50% 1 when you measure it. And then if we apply H again, it brings us back to 0. All right, let's try it out. So go back to your browser. Hopefully you didn't close it out. Go back to your Jupyter notebook. And by the way, if it kind of like freezes on you, you might be able to restart the kernel, and that might get it unstuck. So, but yeah, let's try the X gate. So define a new operation. And we're going to just allocate a qubit just like we did before. But now we're going to apply the X gate to it. So as you might expect to do that, we just say X qubit. It's like calling a function, but it's an operation. And then we're going to, after we apply the X gate, then we're going to measure. And then output the result or print the result. And then what I want you guys to do as well is apply the X gate again, measure again, and then output the results again. So you can see it toggle between 0 and 1. So I'll give you guys a second to do that, and then I'll. Would it be helpful for you guys to see the Jupyter notebook example, or is this slide better because it has the description? I realize you're trying to type in the Jupyter notebook, and then it might be hard to do the chat as well. But all right, I'll give you guys a second. See, that's a little better light here. All right, how are we doing on the X gate? Give me a thumbs up or an X or something. All right, some are getting there. So you should see this output if you did the message in the same way. Anybody getting any like syntax errors or anything that you're having trouble with? Okay. So I guess we can move on to the H gate if there's no other questions on the X gate. Is there anybody who's lost and wants to rehash something? Don't be shy, because I mean, there's not that many of us, so. All right, let's move on then. So this one, we're going to explore the H gate, but really we're going to use that to look at superposition and how it works. So again, I'm going to define a new operation. Oh, I was putting my mouse on the wrong thing. We're going to find a new operation, allocate a qubit, and then we're going to define a new type of variable called a mutable variable. Q# is a little bit weird. The default variables that you define with let are actually immutable, so you can't reassign them. Like once you've once you've created them, you can't like change them. So if you want a variable that can change, you need to use the mutable keyword. So what I want to do here is measure a qubit in superposition a bunch of times and see how many times we measure one. So I'm going to define a variable num1s, start it at 0, and then we're going to create a for loop. And this might be a little bit weird way of defining for loop, but basically this is a range 1 to 100, and it's an inclusive range. And this could be I, any variable. I just did the underscore because we're not really using the iterator variable. So it's just like a personal preference, but you could put anything right here. But this is just the syntax that Q# uses for variable in range. So we want to do this loop 100 times, or you can do it however many times you want, really. But inside the loop, we're going to apply H to the qubit, and then we're going to measure the qubit. And you could do this in multiple steps if you want. I kind of did it in one fell swoop. But we're going to measure the qubit, and if it's a 1, we're going to increment the counter. Now, what is this X here for? I mean, kind of says it, but. So what it says is, measure the qubit. If it's a 1, increment the counter with set and apply X to return it to 0. Why do we need to do that? Anybody know or have a guess? Yeah. So you guys are all on the right track, right? So first of all, so first of all, you guys are right. We want to return it to 0, because what we're trying to do is start out with a 0, right? The qubit starts out as 0. We apply the H to get plus, and we want to measure it a bunch of times. Now, you can actually apply H to any qubit, right? You can apply any gate to any qubit in any, at any state, right? So you can apply H to 1, you can apply H to plus, you can apply H to any arbitrary state. So that's not our intention, right? Our intention is to bring it back to 0, apply H again, and then measure it. Now, somebody else, I can't remember, Harrison, brought up, so we can end the qubit or deallocate the qubit. Exactly, that's another reason, right? We need the qubit to be in the 0 state before it can be deallocated. In fact, if you wanted to, you could allocate the qubit inside of the for loop, and then deallocate it every time. But it's just, more convenient, I think, to just allocate it up here. And then at the end of the for loop, just print out the number of 1s that we measured. And so let me know what you guys get, what numbers you get. $48. Yep. So you'd expect to get something around, or if we actually counted up everybody's, you'd expect it to be a random distribution, a normal distribution around 50. Or what is it? No, not a normal distribution. What is it? Binomial distribution? I don't know, whatever it is. 50-50 shot, right? It's a coin flip. Let's see what I get. We already did explore X, explore H. Oh, last time I did this, I got 45. Let's see what I get this time, 53. Okay. Any questions up at this point? Anybody wondering, whether quantum computers are just a glorified coin flipping machine and what this is all about and why we're wasting our time on this? So if you are wondering that, then that's what we're going to talk about next. Multi-qubit gates. This is where we start to have some power with quantum computing. So, question for you guys: how would you translate this program into quantum software? So we have two variables, A and B, initialize them to false, but doesn't matter. I mean, just they're Boolean variables. And then we have an if statement. If A is true, then we're going to flip B. So we're going to toggle it. We're going to say, well, B, if it's false, it's going to be true. In this case, B is going to become true. Well, it's not because A is false, so this if statement is not going to happen. But anyway, how would you do this in Q#, do you guys think? So it's going to look something like this. Okay. So this might be a little bit new. This is just, we can allocate 2 qubits at once. But yeah, we're going to say if we measure A and it's a 1, then we're going to apply X to B. So can anybody see anything wrong with this code? If we were to, like, say, apply this in the middle of a quantum algorithm. So what's wrong with this is that we're using measurement. And measurement destroys any superposition, right? When we measure a qubit, we measure a 1 or a 0. Not only do we measure 1 or 0 with some probability, but the act of measuring it actually changes its state. It causes it to be a 0 or 1. Right? And that's just how it works. That's just how quantum physics works. So this is a problem. We don't want to measure in the middle of our computation. So I'm going to introduce a new principle that is going to allow us to do interesting computation like this that doesn't require us to measure. It's going to allow us to have qubits to interact with each other. So when multiple qubits interact, their states can become dependent on each other. Let me give you an example. So suppose you have a 2-qubit system. In a 2-qubit system, we have 4 possible measurement outcomes: 0, 0, 0, 1, 1, 0, and 1, 1. So as we saw with the 1-qubit system, just a qubit, right? It could be in a superposition of these during computation, just the same as with a 1. So for example, you could have this state, which is, it looks a little bit like plus, but it's actually called a Bell state. But anyway, you have 1/√2, 0, 0 plus 1, 1. So what does this mean? Does anybody know what this means, this state vector notation? Or can anybody guess? I know we didn't obviously go into the syntax in detail, the math syntax in detail, but can anybody guess what this means? So remember, when we measure, the probability of measuring an outcome is the amplitude or coefficient squared. And these terms of the superposition correspond to measurement outcomes, ultimately. So if I measure this state, I'm going to either measure 0, 0 or 1, 1. So when measured, either both qubits will be 0 or both will be 1 with a 50% probability. So this is what the kind of matrix looks like. But this is actually kind of interesting because these 2 qubits cannot be separated into independent states. So what we'd say is that these 2 qubits are entangled. If you've ever heard of quantum entanglements, this is what that means. So what we're talking about here is if I measure the first qubit, let's say I measure the first qubit only, and I measure a 0. Okay, well, now I know what value the other qubit is without having to measure it. In fact, we've collapsed the superposition of the entire two qubit system. In other words, both qubits are 0 now, even though I'd only just measured one of them. So this is that, you know, spooky action at a distance you may have heard from Einstein. All right, let's do some examples or do a little bit of a quiz. So I have some state vectors here. And the question is, for which of these are the qubits in it entangled? So what about this first one? 1 over root 2, 0, 0 plus 0, 1. And the hint here is, if you measure one qubit and it tells you something about the other qubits for sure, then they're entangled. If not, then they're not entangled. So Daniel says not entangled. Does anyone think they are entangled? Or does anyone else think they're not entangled? Why aren't they entangled? You don't get any information about the other by measuring one of them. Exactly. In fact, the math just works like this, right? We can factor out the 0. So if we factor out the 0, we have 1 over root 2. You know, we have the first qubit is a 0, and the second qubit is 1 over root 2, 0 plus 1, which is just plus. So there's no entanglement. I'm always going to measure 0 in the first one, no matter what. So it doesn't have any effect on the second qubit. All right, what about this second one? By the way, this little O times is the tensor product. And so you don't really have to worry about that right now, but just in this context, it just means that the two qubits are independent and one can be factored out from the other. Entangled, one qubit is always negation of the other, right? So if I measure the first qubit and it's a 0, I know the second qubit is a 1. If I measure the first qubit, it's a 1, I know the second qubit is going to be a 0. So the two qubits will always be different when measured. All right, what about this third one? Now we're getting a little tricky here. We got 4 terms. And I just want to emphasize, you know, well, first of all, if people have questions, please don't be afraid to ask, or if you're lost. But just keep in mind, the terms of these superpositions correspond to measurement outcomes. So if I measure it, if I measure this system, 2-qubit system, I'm going to measure one of these 4 states with some probability. Okay, one person says entangled. One person says not entangled. Okay, why is it entangled? Why is it not entangled? Non-entangled probably is 1/2 whether you collapse the other one or not. Right, so it's not really, I mean, the amplitude is not that important here. Basically what we see is, you know, the thing we could see from the amplitude is, okay, each of these states is equally likely. They're equally, you know, 25%, 1/4. 1/4 of the time, we're going to measure 0, 0, 1/4 we can measure 0, 1, 1/4, et cetera, et cetera. But the reason why it's not entangled is because, can you repeat what the different states mean when there's 2 values between? Oh, again, this is just, we're saying we have 2 qubits in the system. So now instead of just 1 qubit, we have 2 qubits. So when we measure the whole system, like we go through, we measure all the qubits, then what this is saying is that this means that we have, you know, a 25% chance, you know, 1/2 squared is 1/4, right? We have a 25% chance of measuring 0, 0. We have a 25% chance of measuring 0, 1. We have a 25% chance of measuring 1, 0. We have a 25% chance of measuring 1, 1. But before we measure, I mean, this is the state that the system is in, right? So after we measure, it's going to be in one of these guys, 100%, right? But before we measure, so anyway, this is not entangled, right? Because if I measure the first qubit, let's say, and I get a 0, well, it doesn't tell me anything about the other one. It's still 50% chance that I'm going to get a 0 or 1 with the other qubit. So this is, I mean, you can actually factor this out, and you can see this is just 2 plus qubits put together. So there's no entanglement. One does not depend on the other. All right, what about this guy? So now we have 3 qubits, okay? So you can add as many qubits as you want, right? But we tend to describe the state of the whole system, right? We oftentimes, particularly if you have entanglement, you need to be able to describe the whole system at once rather than as individual like qubits. So what about this one? Is there entanglement here or no? Yes, entangled because it's like 0, 0, and 1, 1, but 3D. Exactly, right? So it's this pretty similar situation, but we just have 3 qubits. So if I measure any of the 3 qubits and I get a 0, I know the other answer is also 0. If I measure any of the 3 qubits and I get a 1, I know the other ones are also 1. So the qubits, 3 qubits will always be the same one to measure. Okay, what about this? This is a really challenge one, the tricky one. Oh, this one. I'm putting my mouse on the wrong screen here. Sorry. What do you guys think? Not entangled? Why not? Suppose I measure the first qubit and it's to 0. Then what? In fact, suppose I measure the first qubit and the second qubit and they're both 0. Does that tell me anything about the third one? Yeah. So these qubits are entangled, maybe in a slightly more nuanced way than some of these other examples, but yes, there's entanglement here. So if the first qubit is a 0, the other 2 will be the same as each other. If it's a 1, the other 2 will be different from each other. So if we measure the first qubit to be 0, we're in this land here. And if it's a 1, we're in this land. 0, 0 plus 1, 1 versus 0, 1 plus 1, 0. So it's almost like if we measure it to be a 1, it's like this guy. And if we measure the first qubit to be 0, we're like this guy. Okay, does anybody have any questions on this, on entanglement? Measuring 1 does not entangle the other 2. They're already entangled. So when you use entangle as a verb, you're saying that you are causing the qubits or causing the quantum states to be dependent on each other, so that you could take one and put it on the other side of the universe as the other, and you still have that relationship, that entanglement, where if you measure 1, you know the outcome of the other. What you can have actually is if you measure a qubit, it could destroy the entanglement because it takes away the superposition that you have. So like, for example, you could have 2 qubits that are entangled. Let's say they're in let's say they're in the first Bell state here. Let's say they're in this. So either they're both 0 or they're both a 1. Now you put them on the other side of the universe and you measure one of them and it's a 0. Well, the other one's a 0, fine, okay. But now suppose you start making changes to the first one, right? They're no longer entangled, right? You can measure the first guy as many times as you want. It's not going to make a difference to the other guy. So that's kind of important, really, because I think one of the things that people misunderstand about entanglement or like quantum teleportation or some of these things is that, oh, well, you could use that to like transmit information faster than the speed of light. No, you cannot. Right? You cannot use the principles of quantum mechanics to transmit information faster than the speed of light, because that's not what entanglement is. It's not an information transfer. Now, it is spooky because it does seem like, you know, the one qubit is having an influence on the other, but you really can't think about it that way. Really, what you have to think about it as, okay, these two qubits have now become entangled. So I can really only describe the system as a 2-qubit system now. I can't describe the system as 2 different qubits. Although you can measure one, and then that causes, you know, that collapses superposition. But did that answer your question, or did that just cause extra confusion? So, all right, let's move on. So the reason why I'm talking about entanglement and multi-qubit gates is that while multi-qubit gates can produce entangled states. So here we have a multi-qubit gate called the controlled X, or C naught. And this is a gate that the way you can think about it is applies X to the target qubit if the control qubit is a 1. So this is the magic sauce that we were looking for earlier with, like, okay, if this guy is a 1, flip the other guy. So this is it, right? But it does it without measurement, right? So here's an example circuit. This is a quantum circuit diagram. So we have 2 qubits that start in a 0 state, and then we apply H to the first one. So now we're in that plus state, that 50% 0, 50% 1. And now we apply a C naught with the first qubit as control, the second qubit as the target. And now we get this state out, because what we say is that, well, if the first qubit was a 0, then the X did not happen. So the second qubit is also a 0. If the first qubit was a 1, then the X did happen. And so the second qubit is also 1. So either they're both 0 or they're both 1 with 50% probability. Did people follow that? Does that make sense? And again, I mean, when I give you the slides, you can kind of look in the appendix and see the math behind it, but the math is not super important. All right, let's try this out. I think it's going to make more sense when you can actually try it in Q#. All right, so go back to your browsers, and we're going to try C naught, explore C naught. So define a new operation, and then we're going to use this syntax that I kind of showed earlier to allocate 2 qubits. So, I mean, you could do this on 2 lines if you wanted to, but this is just a concise way to allocate 2 qubits. And you call them whatever you want. Here, I'm just calling it control and target, and then apply X to the control. So the control is a 1, and then apply C naught with the control as the control, target as the target, right? And then see what we get on the target. Well, what do you guys expect? I mean, expect it's a 1, right? Because if it's a 1, if the control is a 1, we expect to flip the target as well. This reset all is just a helpful operation that's provided by Q#, which resets all the qubits in the array that you give it. So this is kind of a new concept as well if you haven't played with the arrays, but it's just like a list of qubits. So you can use these square brackets. And so this is an array of qubits. We're passing into reset all. Reset all is going to go through each, measure each one, and if it's a 1, it'll flip it to 0. So this is a dangerous operation, or not a dangerous, but it's a destructive operation. It destroys any superposition you have. But that's, in this case, this is what we want. We want it to get everything back to 0. Oh yeah. There's a little note to tell you that, in case you were listening. And by the way, an array of qubits is typically called a register. So later on, you could have allocated these qubits in an array if you wanted to, but felt it was simpler to just do 2 single qubits. But later on, we might get to arrays of qubits. And in the literature or whatever, you usually see it as a register, or defined as a register. Okay, how are people doing on the C naught? This one is straightforward. Hopefully you understand that since we have the first qubit is a 1, we're just going to flip the second one because that's how C naught works. Right? Like if the first is a 1, apply X the second. All right, we good on this one? Give me a thumbs up or thumbs down or something. Okay. So this one is a little bit trickier. So now we're going to set up an entangled state. So that last one was no entanglement, right? We were literally just flipping between 1 and 0. But now we are going to set up that circuit that I showed a little bit ago, where we're going to create an entangled state. So to explore entanglement, we're going to have a new operation. And oops, I changed this, but I got to fix that. I'm just allocating the qubits in the same way as the other one, not using an array, just control and target qubits. But then now we're going to do a for loop just like before. And you can do as many times as you want. I'm printing something out every time, so I just only wanted to do 10 this time. But apply H to the first qubit, which is going to take it from 0 to that 50% 0, 50% 1, that plus state. And then we're going to apply C naught with the control as a control, target as a target. And then we are going to measure both qubits and see what they are. And let me know what you guys get. And then if you did that already, there's your extra challenge. $404. Uh-oh. Try refreshing or something. One thing you can do too is like you can download your notebook and then to upload it later. You can also, if you go to the Q#, if you just Google Q#, you can figure out how to run the Jupyter notebook locally. But you probably don't have time to do that right now. But that's what I'm doing. I'm just like running it in a Docker container. Hopefully everyone's not getting 404. Hopefully the server didn't crash. All right, so give me a thumbs up if you are done. And actually, no, better yet, type in the chat what you get when you're done. And this is kind of a good time. It's 7:07, so might take a minute or two and stretch. This is a good opportunity. If you're lost, please ask questions. Most of you said you've never seen quantum before, so I'm expecting that many of you are grappling with this. Oh no, did Binder crash? That's not good. Yeah, I don't really have a backup plan for that. I mean, I could show you guys my code and see what happens. Starting a new notebook. Yeah, you might have to do that. I think part of it too is like if you are inactive for too long, it kicks you out. And I think the timer is like way too short. It's like 5 minutes or something. Yeah, that's too bad. But hopefully if you start a new notebook, then that'll work. I will give you guys the slides. So I think Kim has a link. Uh-oh, syntax error. Invalid initializer expression. Possible initializers are qubit or tuples thereof. So sorry, I think the colorization is a little bit off here. I don't know why this is like some error with the Jupyter syntax highlighter. This parenthesis is to be black, but anyway, yeah, you need to have these parentheses. Oops. You need to have these parentheses for it because it has to be like a tuple. It doesn't know that you want it to be like, you want this to match this and this to match this, so you don't have the parentheses. Ooh, that's exciting. So it looks like you got 1, 1 4 times and 0, 0 6 times. But, oh no, oh yeah, a lot of people are getting similar stuff, okay. So what we should see is that we should always have either 0, 0 or 1, 1. We should never have 0, 1 or 1, 0. Right? So this is what it really means to be entangled. Okay, so did anybody get the challenge? Add one line of code so the 2 qubits will always be different instead of always be the same. And I mean, if you do end up doing it multiple lines of code, that's fine too, but you only really need one. Any ideas? Exactly. So you can just apply X to either of the qubits. So here, let me actually show that. So here we have explore entanglements. I'm gonna run that. Here you can see this is my last run. You get 0, 0, and 1, 1. But now if we apply X, you can do it really anywhere, but we could just do it here. Apply X to the target. Okay, and then simulate, we're getting 0, 1, and 1, 0. Yep, yeah, you could do it after the C naught as well. Doesn't matter. Cool. All right. Does anybody need like a minute or something, or any questions at this point? All right. I think we can move on. So this is going to get a little bit trickier. So if you thought that was really tricky, so get ready. So the next section we're going to talk about, this is really the last key concept in quantum computing and quantum physics. And this is a concept of phase and interference. So the idea of phase interference is not that new. It's there in a lot of engineering. Basically, what this concept is that signals with the same frequency interfere with each other based on their phase. So we can have constructive interference, which means if they have the same phase and they're added together, now you have a larger signal. It amplifies the signal. So this is like a hearing aid that amplifies certain frequencies. Or you can have destructive interference, which is when the two signals have opposite phase or they're out of phase. And when you add them together, you have nothing. It just cancels out. This is like noise canceling headphones, which are pretty amazing, actually. I think noise canceling headphones are really unbelievable how well they work. But yeah, that's exactly what's happening. It's basically you're generating a signal which is exactly the same but in the opposite phase, and then playing it back to have destructive interference. So hopefully you all have, I think, probably seen something about interference like this before. So we have the same concept in quantum computing, which seems weird, but I'll explain how it works. So in quantum computing, when we're talking about phase just refers to the sign of each superposition term. So I think we saw a state earlier that had a negative sign here, but this is just, a negative phase here in the one term. So these are two different states because they have, different phase, even though when we measure them, we're going to have the same type of outcome. 50% of the time we're going to get 0, 50% of the time they're going to 1. But these are actually different states, and that matters for computation. One thing that I haven't talked about yet is that this side of the unit circle is not used in quantum computing because if you have the state A, B, it's the same as -A, -B for all intents and purposes. So we just ignore this side. Another way to say that is the relative phase between the terms matters, but a global phase that is like a sign that cannot be factored out of the superposition does not matter. Since we can factor out the negative here, it doesn't matter. Could ignore it. Okay, so we actually have quantum gates that can be used to manipulate and detect phase, and namely Z, which is a phase flip gate. So here's the definition again. Quantum gates are defined as matrix operations or matrices. This is a symbol, and the Z gate can be used to toggle between plus and minus. In fact, it flips over this line. Now, going back to the Hadamard gate, I think we talked about, well, you can actually apply the H gate to any qubit. It doesn't have to be a 0. So if you actually look at what the Hadamard gate does to a 1, remember, really geometrically what the Hadamard gate does is it flips over this line. So yes, it toggles between a 0 and a plus, but it also toggles between a minus and a 1. So it's kind of a multi-purpose gate. I mean, really, again, like I said, it's just a matrix transformation. So you can apply this gate to any qubit in any state, but these are like the important states that I want you guys to understand. All right, so I know I said I was going to avoid some math for this, but this is like the one math slide, so get ready. So to see what happens when a gate is applied, what you have to do is distribute the gate to each term in the superposition. So here I'm going to go through a quick demonstration of why, or do you guys remember what H of plus is? Like when you apply the H gate to plus, what do you get? I just had it on this last one. When you apply H to plus, you should get 0. Yep. So why is that? Algebraically, I'll show. And remember that we say that H of 0 gives you this state here, 1 over root 2, 0 plus 1. And H of 1 gives you 1 over root 2, 0 minus 1. So here we have H plus, which is the same as H of this state here. This is plus 1 over root 2, 0 plus 1. And what does it give us? Well, we can distribute the gate to each term in the superposition. Oh, the color coding got a little bit off there. That's annoying. And we say, okay, H of 0 is this one, H of 1 is this one. So what we get is this. So we have 1 over root 2 from here, and then this H of 0 becomes 1 over root 2, 0 plus 1, and this orange H of 1 becomes 1 over root 2, 0 minus 1. Okay, so we can factor this out, combine like terms, and we get 1/2 0 plus 1 plus 0 minus 1. Well, 1 minus 1 is nothing. It goes away. So the zeros constructively interfere and the ones destructively interfere. So we get just 0. Did people follow that? So a little bit of math, a little bit of algebra, but this is what we really mean when we talk about interference in the context of quantum computing and quantum physics. This is the same principle mathematically that we get the interference pattern in the double slit experiment. If people are familiar with that. If you're not, it's fine. Okay, so here's a little quiz. So what is the state of the system after each gate or set of gates? So here we go. After H and X, well, an H applied to 0 is going to give us plus, and an X applied to 0 is going to give us 1. So we kind of know that already. And if we write that out, the full state vector expression of this is 1/√2, 0, 1 plus 1, 1, right? Because the second qubit is always going to be 1, and the first qubit is half the time going to be 0, half the time is going to be 1. So this is the way to describe it fully, the 2-qubit system. Okay, so what happens when we apply this controlled Z? A controlled Z gate, because we just talked about the Z gate, controlled Z gate flips the phase of the term of the superposition when all controls and the target are 1. So it's kind of like the controlled X in the way that, okay, if the target's a 1, then apply Z, or sorry, if the control is a 1, then apply Z to the target. So this is like that, right? If the control is a 1, then apply Z to the target. But if the target is a 0, a Z gate does nothing. Z of 0 does nothing, right? So go back to this. Oops. Uh-oh. Let me have to go back a couple things. So since it flips across this line, Z of 0 does nothing. So the controlled Z only does anything if both the control and the target are a 1. Does that make sense? And yeah. All right, so this might be a little bit confusing. So does anybody have any idea what's going to happen after this? What these qubits are going to be after we apply the controlled Z? The control, this is the control and this is the target. Whenever you see these like dots, that means the operation is controlled on where the dot is. All right, so Alejandro did get it right. So I wonder if he knows why. Probably he does. No, it doesn't make the bottom one 0 because a Z of, when you apply Z to 1, it doesn't make it a 0, right? It makes it a -1, except there is no -1, right? So I'll just explain what happens. It's a little bit nuanced. So yes, the first qubit is going to become a minus, and the second qubit is going to stay a 1. The reason why that happens is this. So we have a controlled Z, I'm just denoting that with CZ, on this state, because we just said this is the state, what the state was before. And remember, to see what happens, we have to distribute the gate to each term of the superposition. So we're going to say, okay, we have 1/√2 CZ of 0, 1, or controlled Z of 0, 1, plus controlled Z of 1, 1. And remember what I said was, it's only going to flip the phase or the sign of the term if both the control and the target are a 1, or really if all the controls, because you can have multiple controls, and the target are 1. So this is not going to do anything because the control is a 0, but this is, because the control is a 1 and the target's a 1. So this is going to flip the sign. It's going to flip the phase here. So now we have 1/√2, 0, 1 minus 1, 1. So it's just like the state, but we have a minus here. And we can just factor this back out, right? You just take this 1 back out, and then we're left with 1/√2, 0 minus 1, which is just minus. So this is a little bit weird because the idea of a control and a target makes me think that, okay, the control is never going to be modified. But this is in fact what happens. It's a little bit, I find it to be slightly a misnomer. But this is what we have. This is called phase kickback, is the phenomenon. This is the how it's referred to. So then what we see is when we now at the end, we apply H and X, well, the X gate puts this back into 0. But what we see is when we apply H, remember H toggles between 0 and plus, but it also toggles between minus and 1. So if we apply H again, we're going to get 1 at the end. So this is a way of detecting a phase flip. We've detected that this first qubit had its phase get flipped. Okay, so let's try it. Let's go back to your browser. Hopefully you don't get a 404. Hopefully you were interacting with it slightly so that it wouldn't time you out. This is a little bit of a longer one, but it's actually not that complicated. So we're defining a new operation, allocating a qubit, just like we have been. And then we're going to do something a little bit weird. We're going to apply H and then Z and then H again. The reason why we're going to do that is because the H gate is going to put the qubit into the plus state. The Z gate is going to put it into the minus state, because remember the Z toggles between plus and minus. And then the H gate is going to take the minus and hopefully put it into a 1. So this is just, we're doing this because the only way we can actually measure it is if it's a 0, 1. We can't measure whether it's a plus or a minus. So the way we can determine whether it's a plus or minus is by using these H gates to kind of translate it from phase to like amplitude, I guess. So what do you guys get for this? I know you're probably typing. And while you're typing, so here's the question. What single gate is equivalent to HZH? Yeah, X. It's the same thing. And you can actually do the math out, right? If you multiply out HZH, you're going to get the same matrix as X. At least I think so. I haven't actually done the math, but. All right, so let me just show you what I get. Hopefully you guys get the same thing. Oh yeah, explore Z. So HZH of 0 yields 1. HZH of 1 gives me 0, just like X. All right, you guys good? You want to go to the next one? You're still working. Give me a thumbs up or thumbs down. All right. Getting some thumbs up. So this is a pretty straightforward one because it's just kind of like the X example, but with HCH. This next one is going to be your first really challenging one. So I'm not going to tell you to code until you get the chance to try it. I'm just giving you the circuit diagram. This is the same circuit that we had that example, this phase flip detection circuit. and see if you can write the code to do this. So I've given you, you're going to allocate control and target qubit, but then figure out how to apply H to the first qubit, X to the, or H to the control, X to the target. You're going to do control Z. Oh, you can use CZ for control Z. It works like C naught. I'm pretty sure you can do CX as well. I think that's something in Q sharp for C naught. But yeah, your goal is to get this output 1, 0, just like we saw in the example. And give me a thumbs up when you're, or a check mark or something. I think the thumbs up disappears, so give me a check mark when you're, when you got it. And by the way, you know, there's not that many of us, so if you run into an error, please, you know, you can hop on the mic and we can debug. Or if you're confused. All right. How are you guys doing? Any progress? Did anybody get it? Not yet. All right. I'll give you some more time. I won't rush you. We still have, I think, a half hour. So. Daniel's got it. So if you don't want to see the solution, look away. But yeah, apply H and X, H to the control, X to the target. I'm going to apply CZ, and then apply H and X again. So you find that when you're doing quantum software development, having a circuit diagram is like gold. It's awesome. Unfortunately, a lot of the research papers do not give you a circuit diagram. So, so this is a problem. In fact, this is something that MITRE is looking to address in research. Okay, those of you that are done, here's a question. What happens if you remove the X gates? And why, I guess? Superposition is always the answer. It's like C or D, none of the above. So I'm just try it. I mean, try it in your code. Like comment is // comment out the X target and X target here. See what happens. Or I could just show you guys. So here we go, detect phase flip. So right now when I simulate it, I get 1, 0. So if I comment this out, what do I get? 0, 0. So why is that? Let me go back to the circuit diagram. So instead of a 1, I get a 0 here. What does that tell us? Entanglement is the other, catch-all. You can always answer entanglement and it'll work. So it's actually there's no entanglement. There's nothing happening, right? If this qubit here is a 0, if these X gates aren't here, well, first of all, the answer to my question of if this is a 0, what does that tell us? Well, it tells us that no phase flip occurred. Right? This is a phase flip detection circuit. Okay, so if we measure 1 here, because we have this H here and here, right? If we measure 1 here, then we know that there was no phase flip. So why wasn't there a phase flip? Well, because the controlled Z only does anything if the target is a 1, right? It only, if we go back to the math here, okay, it only flips the phase or flips the sign of the terms of the superposition where everything is a 1. So if the target is a 0, the Z does nothing. Remember I said that a bunch of times? Oops, went too far. Oh no. The Z flips the stuff over this line, flips the state over this line. So if we're on the line, if we're already 0, it does nothing, has no effect. So because it has no effect, it has no effect on the control either. But anyway, that's neither here nor there. So did everybody, was everybody able to get this circuit implemented in software? Is anybody lost or have questions or wants me to explain anything again? Give me a few thumbs up. I'm more curious about any thumbs down. I haven't seen a single thumbs down or X or anything through this whole workshop. So you guys are very shy, or maybe you're all geniuses. I don't know. Maybe you're already quantum experts. This is all just so intuitive.
All right. Real quick, could you go over what CD does after you define H and X?
Yes, CZ stands for controlled Z. And what that means is it's going to flip the phase, in other words, flip the sign of the term in a superposition where both the control and the target is a 1. So the way you can think about it, I mean, the way I explained the controlled X or the controlled the C naught was, hey, this flips the target if the control is a 1. Well, it's similar to that. Like it applies Z to the target if the control is a 1. But the thing is that the Z only does anything if the target's also a 1. Whereas the X, it flips the 0 to a 1 and back, right? So the way to think about the controlled Z is it really only does anything if both the control and the target are a 1. So it's not, if you're not following that, that's fine. I certainly did not get this the first 10 times I heard it. So I'm just, After this, I'll give you the slides. You can go back and rehash it. But the cool thing about doing the software is that you can actually write the software and simulate it and see what happens. So really what we see happen is that this CZ, we can see that it flips the phase of this first qubit. It turns it from a plus into a minus. And we know that because when we apply a H gate, we get a 1 when we measure it. Because when we apply H to a minus, we get a 1. If it were a plus, if it didn't do anything, if this controlled Z didn't do anything, then we would get a 0. That's what I was explaining when I said, hey, what happens when you remove the X's? Did that answer your question?
Yeah, that makes sense.
So if both control and target are 1, does it flip both phases? So again, so the thing about phase is it only matters, only the relative phase matters between terms of a superposition. So if you have just like 2 1 qubits that are just hanging out and you apply Z to either of them, you apply control Z, whatever, it's not going to do anything, because if you flip the phase of a 1, it's just a -1, which is the same, right? It's not anything, like there's no superposition there anyway, right? The phase only matters when you have superposition, which is why we set up this like before and after H and X, right? Or before and after H anyway. So the H puts the qubit into superposition. The control Z flips the phase of like one term of the superposition, or flips the sign of like one term of the superposition. And then now we use the H gate again to bring it back out of superposition, and we can detect whether a phase slip occurred. Let's move on, because this is definitely like the most confusing part. But it's also, it's not critical that you understand in detail how this works. It's just, you got to understand that, okay, there's something that is phase, and different terms of a superposition can have a different sign, and that matters because we can actually detect when the phase slip occurred. We can also have constructive and destructive interference. And in fact, this is how we achieve useful computation, is by taking advantage of these things. So this next part we're going to talk about, this is the last section, where we're talking about, okay, why do quantum computers actually matter? Like, why do we care about all this stuff? I just told you all the principles behind and all the the fundamentals behind quantum computing, but so what? So just like we have classical algorithms, which are step-by-step instructions for how to solve a problem on a computer, on a digital computer, we have quantum algorithms, which use superposition, entanglement, and interference, the concepts we talked about today, to process information in clever ways. And this has applications all over the place, from crypto and cyber, machine learning, simulation, chemical simulation, biological simulation, optimization, route optimization, data and image processing, and many more things that we have yet to imagine. And in fact, if you've studied algorithms, what we actually say is that quantum computing and quantum algorithms live in a different complexity class than classical algorithms. So if you've ever heard of like P and NP complete, this means like I can solve a problem in deterministically in polynomial time, versus I can't solve it deterministically in polynomial time, would be NP. You can have problems which are NP, but can be solved in a bounded error, in a deterministic way in polynomial time on a quantum computer. So you can have, for example, problems which are exponential in classical, but are polynomial or linear in quantum. It's a narrow set of problems, right? It's not every problem, but there are key problems for which that's the case. For example, there's an algorithm called Shor's algorithm, which can factor prime numbers in linear complexity versus in classical land it's exponential, and this breaks RSA encryption and public key, a lot of public key crypto systems that we use today. So like your HTTPS, the encryption protocol that you use to go to your websites, quantum computing breaks that. So get ready. So here, I'll give you though a simple basic example of a quantum algorithm. This is a toy algorithm, so it's not that serious, but it is, it works quite amazingly, and hopefully you'll be able to follow how it works. So consider the following problem. You're given a black box function that outputs 0 or 1 based on a binary input, and you are promised that it is either constant, which means that it outputs the same value for all possible input combinations, or it is balanced. It outputs 0 for exactly half the input combinations and 1 for the other half. So this would be like a truth table for an example of a constant function. It always outputs 1 no matter what. And this would be an example of a balanced function. It outputs 0 for half the inputs and 1 for the other half. It doesn't really matter. This could be like this 1 and 0 could be swapped. That would still be balanced. Right? So this is kind of a contrived problem, but this is a problem we're going to start out with. So the question is, how do you determine which one it is, constant or balanced? You're given this black box function. You're told it's constant or balanced. How do you know? And how quickly could you find out if you were on a classical computer and you're given this function in classical land? What do you guys think? Do you guys understand the problem, the question? Yeah. Yeah, so in this case, right, if you had these, like it's just two bits of input, you could try 0, 0 and you get a 1, and you wouldn't know that it's constant or balanced, right? I mean, in this case, you get 0, but that wouldn't tell you anything, right? You could try 0, 0 and then 0, 1, and you could get a 1, 1 here. It wouldn't really tell you whether it's constant or balanced because maybe you just got unlucky. Here you would get 0, 0. It could still be constant, right? Because you're still getting all zeros. In this case, you need to do 3. Try 3 inputs. Now, generally, you need to try half the inputs plus 1 in the worst case, right? I mean, in this case, like if I tried 0, 0 and 1, 1, I got a 0, 1. Well, I know it's balanced because it's not constant. It's not giving me the same every time. So yeah, just to recap. So this is a contrived problem, but the problem is somebody comes along and gives you a function. You don't know how the function is implemented. You don't know anything about it. All you know that it has one of 2 properties. Either it's constant or balanced, and constant is defined as it always gives you back the same input. So it's either always going to give you back a true or 1, or it's always going to give you back a 0 or false, whatever. And then a balance would be you put in all the inputs, and half of them you get back a 0, and half of them you get back a 1. Okay, so the answer, I mean, how quickly can you perform it, the necessary computation on a classical computer? You need to query this oracle at a maximum, or not maximum, but in the worst case, half plus 1. Or if you give in n bits, it would be on the order of 2 to the n, so exponential. So amazingly, okay, a quantum computer can solve this problem in 1 iteration, or 1 like query to the oracle or the black box function. So the problem can be solved exponentially faster on a quantum computer if the function is provided as a quantum oracle. So a quantum oracle is like a black box function, but typically a quantum oracle, the way a quantum oracle is implemented, typically it phase flips the target based on the input. So instead of having like an input and an output, right? In a quantum algorithm or quantum process, you have to have the same number of inputs and outputs, right? Because remember, you're not like consuming signals and then reproducing them on the other side. You just have qubits that are passing through and the factory is going to work, right? So if we want to have an output, really, we just need to have a target, or you could call it output, you call it whatever you want, but it's technically an input and then it gets passed through. So here's an example for 1 qubit of how this would work, how a quantum computer could detect this. So this is really like our phase flip detection circuit. So this is an example of a quantum oracle, which is 1 input qubit, right? We just have 1 line here, and that is constant. The reason it's constant is because it always phase flips the target. It always applies a Z gate to the target, no matter what. It doesn't matter what this guy is. It's always going to apply Z. So you can think of it as it's always going to give you an output of 1, whether the input is a 0 or 1. This is an example of a balanced oracle, because if the input is a 0, it's not going to flip the phase of the target. And if the input is a 1, then it is going to flip the phase of the target. So here is a circuit which can detect whether we have a constant or balanced oracle in this question mark box. Now, this is not that interesting because it's only 1 qubit, but this is the 1 qubit example. People following? Okay, so if you scale this up, you can apply what's called the Deutsch-Jozsa algorithm. So this is a real quantum algorithm that does solve this problem, and you can demonstrate that in software we'll see later. So the way this works is, first you have to assume you've given this oracle, okay? But so assume you have, so you're going to allocate n input qubits and 1 target qubit. So you have, however many input qubits you have, but you also need a target. And then apply H-gate to each input and X-gate to a target. So really what this means is we're going to put all the input qubits in a uniform superposition. In other words, the likelihood of anything being measured, any input combination being measured, is all equally likely. So there's no superposition. They're all, each qubit, if I measure them independently, they're 50%, 0, 50%, 1. Then we're going to apply the oracle under test, and then we're going to apply H to each input qubit again, and measure the qubits. If all zeros are measured, the oracle is constant. Otherwise, it's balanced. So why does this work? Well, the intuition is that a constant oracle is not going to affect the input qubits, because it's either always going to flip this, in which case there's no dependence on any of the inputs, or it's never going to flip this, in which case there's definitely no dependence on any of these qubits. So it's not going to touch the input qubits. It's not going to mess with them. It's not going to do anything. It's not going to flip any of their phases. Okay. However, a balanced oracle, if you do the math out, causes destructive interference on the outcome, which is all zeros. So another thing, another way to think about it in a somewhat intuitive way, and this is kind of something that way people typically describe, like the idea of quantum parallelism, is if you think about this oracle, this oracle has input and output, and in classical world, you can only put in 1 input at a time, right? I'm going to say, okay, the input is 0, 0, 0, 0. What's the output? And then you get the output back. Now I'm going to say the input is 0, 0, 0, 1, and now I'm going to get the output back. Now in quantum, you are not limited to putting in 1 input at a time. You can put in all the inputs at a time. In fact, that's what we're doing here. Okay, we're putting in a superposition of all the inputs. So what you see is that it's like the function or the oracle is computing on all the inputs at once. Now, the hard part is once that is done, how do you get out some useful information? Because remember, once we measure, superposition collapses, we only get one answer. So this is really the fundamental insight or genius behind all these quantum algorithms that are out there, is each of them figures out a way to leverage this quantum parallelism and allows a function to almost compute all the inputs at once, and then you combine the result in a way that gives you some information. So if you're curious about like the details about why this algorithm works, then you're welcome to read the appendix later. But this is the algorithm. So what, in the remaining time, we don't have much time left. I want you guys to do your best to implement this. And I think, maybe if we go over like 1 or 2 minutes, I think we will have enough time. So the first thing we need to do is implement the constant and balanced oracles. So I'll show you. So we go back to our workshop exercises here. Create an operation which is constant. And here, the syntax is a little bit weird because I'm breaking it over multiple lines, but all I'm doing is I'm saying, okay, I'm gonna have two arguments rather. We're gonna have an argument called input, which is a qubit array or qubit register. So like we said, we have like n qubits, we have n inputs. We don't know how many. And we have a target qubit, which is another argument to the operation. And this is constant. So one way of implementing a constant oracle is it does nothing. That's constant. It always does nothing. It always outputs 0, basically. And then here's an example of a balanced oracle. So we have, again, it's the same syntax. We have an input register and a target qubit. And all this does is it applies a Z when the first qubit is a 1. So it's a CZ with the first qubit as the control and the target as the target. Why does this create a balance? Well, because half the time, right, for half of the possible inputs, the first qubit is going to be 0. And for half of the possible inputs, the first qubit is going to be 1. You can see that if you kind of go back to the truth table here, right? That's basically what this is, right? The output is a 1 only when the first qubit is a 1. So in fact, it doesn't matter if we have like 1 million inputs. This will always be balanced if we say, okay, the output is just connected to the first qubit or the first bit. So sorry to jump around the code, but yeah, implement the constant balance operations. And then challenge, probably for later, is create alternative constant and balanced oracles. So for example, you could try to write a balanced operation that phase flips the target whenever there's an odd number of 1s. That's a fun one to try. All right, so give me a thumbs up when you guys have the constant and balanced operations copied over. And let me know if you have questions about why these are constant and balanced or. Okay. So now is the challenge. Implement the Deutsch-Jozsa algorithm. So I've given you the circuit diagram, although there's some ... dots. Okay, and I've given you kind of the scaffolding, but it's your job to implement the core of the algorithm. So just to explain the scaffolding here, so we have a new operation called Deutsch-Jozsa, and this is a little bit interesting. So it actually takes the oracle as an argument. So it takes an operation. This is syntax to say like any operation, where the operations has 2 inputs. One is a qubit array, one is a qubit, and it doesn't return anything. Its output is void or unit. And then we also have a parameter called input length. This is like how many input qubits we have. So you can see down here, I'm I'm allocating a bunch of qubits. I'm allocating the input qubits, and this is a slightly new syntax. This is to allocate a qubit array, and then the target qubit here. So, so yeah, so try this scaffolding, see if you guys can implement this circuit diagram, and return true if the oracle is constant and false if it's balanced. Remember, it's constant if everything is a 0 when measured. And we're running up against time. So look away if you want to try it by yourself. But I think we need to kind of move on and wrap up because I want to show you how to test it. So, oh, I think that's out of order. I wanted to show you guys that you can use apply to each as well. So there's an operation in Q# called apply to each, which you can use to just apply a gate to all the qubits in an array. So it's almost like a for loop that applies a gate to all the qubits in an array, but it's in one operation. It's kind of convenient. So all we're doing here, applying H to all the input qubits and applying X to the target like we see in the diagram. And then we are running the oracle. And then we're doing the same thing, apply H to all the input qubits. But then here, what this is doing is looping through each qubit in the input register and measuring them. If any of them are a 1, then we know we are balanced. So we set the result to false. Otherwise, we don't set the result to false. If they're all 0s, we aren't going to set the result to false. And then when we return, we're going to get false. So there's multiple ways to write this syntactically. This is just one way. So the one thing before you guys go, I know it's 8, is I just wanted to show you how to test and analyze your implementation. So here I'm setting up an operation which calls that operation, that Deutsch-Jozsa operation that we just made. And we are passing that constant operation we defined as a parameter. And 8, remember 8 is just the number of input qubits. So you could do any number really. If it's too many, then your simulation will run out of RAM. But what we expect is, this is kind of a typical way of writing unit tests. You expect this to return false. Sorry, you expect this to return true because we said constant. Return true if oracle is constant and false if it's balanced. So this one we expect it to return true. So if it doesn't return true, then it's a failure. And this one, we expect this one to return false because it's balanced. So if it returns false, then it's a failure. Otherwise, it's a success. So if you did it correctly, then and you write this test and then you simulate it, then you should get a success. The other kind of cool thing you can do as well is use this magic command estimate to estimate the resources, the computational resources that would be required to run this on a real quantum computer. So right now you're just on simulators, on a classical simulator. But if you're actually going to compile this code and run it on a real quantum computer, then you would need, it'll tell you how many qubits you need. You need 9 qubits. You're going to measure 8 times. You're going to have 20 of these are called Clifford gates. And you're gonna have 1 C-naught gate in there. So yeah, Q# includes a resource estimator that tells you how expensive your operation is. You can use this. And why don't I just show you guys that before we go. So we have this constant oracle, balanced oracle or operation. Here's my implementation of Deutsch-Jozsa. And then here's my test. So if I run this test, Hopefully it gives me success. Uh-oh, it's because I didn't run this first. Let's just make sure we run through all these. I think I restarted my kernel, that's why. All right, and then if I simulate, uh-oh. My kernel is sleeping. Okay, I think it did that one. All right, there we go, success. So here, what I wanted to show you guys is that I can estimate the quantum computational resources that be required to run this on a real quantum computer. Use this estimate command. I just set up a very simple operation that just like invokes the Deutsch-Jose algorithm. So then when we run that and estimate it, it'll generate this nice table for us. So the reason why this is interesting is because quantum computers are not that powerful yet. You can do like maybe 50 qubits or so. And so what we want to be able to see is if I implement an algorithm that requires more than, let's say, 50 qubits or whatever the state of the art is, I want to see how expensive it is to actually run so I can make a prediction about when I'm going to be able to unlock that ability, so to speak. So if you remember me talking about the breaking RSA encryption, right? You cannot do that now with today's quantum computers, but we could write a software implementation of that, and we could tell you precisely how many qubits, how many quantum gates, what gate depth you would need in order to actually be able to break RSA encryption. And that's kind of a typical activity that a quantum software engineer might do. They might take an algorithm that is described in the literature and say, I wonder if there's anything to that. I wonder how legit that is. Let me try to implement that in software and see what I get. And so that's part of what I do. And yeah, I mean, I think I really recommend you guys following up with this. Feel free to reach out if you're interested in this stuff or you're interested in MITRE. And we also have a full course on this. So if you want the course taught at Tufts, tell your department heads, I guess, and have them reach out to me. And yeah, are there any other last minute questions on this? I think Kim is going to, she just posted the slides on Box. So please, click the link and download the slides. There's an appendix that has some of the math. So yeah. All right, anything else? I think I'll stop the recording unless there's anything else. All right, thanks everybody for attending. Have a good night.